This video is going to be a little bit more work with ionic formulas, how to make ionic formulas, how to figure out what the charge on the metal is, what the charge on the anion is. Also, we're going to talk a little bit about something called Lewis structures, who's a dead white guy that came up with this really cool way of representing valence electrons and writing structures of compounds. So probably one of the first things that we should mention is that it's really important that you're able to look at the periodic table and pull a charge off the periodic table. Of course, I will provide you with this handout right here that has all the charges on it, but sometimes you need a little bit of extra help to kind of find charge and how that charge relates to the actual formula that we're going to write for a compound. So let's just kind of pick an example. Let's pick out, let's say, an alkaline earth metal like strontium. And then let's pick out some sort of nonmetal. Keep in mind that the nonmetals are usually on the right side of the table, and they're usually the negatively charged things, whereas the metals are on the left side of the table, or at least to the left of that kind of zigzaggy line of metalloids, and they become positively charged. So let's just pick out, let's say a halogen. Let's pick out an iodine. And let's say that the question is asking us, okay, I need to have both of these come together in a compound. What kind of compound is it? That's something that we really have to ask ourselves. And what we're going to learn is that the one question you should always ask yourself before you do anything with compound formation is there a metal present? Because if you find a metal in there, we are going to follow a whole different set of rules. It'll become a lot clearer at the end of these next series of days of video lectures here. So the fact that there is a metal there, I know that that thing is in fact ionic. So all of the rules that I'm going to talk about are definitely going to apply here. If we looked at this thing and didn't see a metal present, for the most part, those are going to end up being covalent compounds that we're going to apply different rules to that'll be available in another day's video lecture. So the fact that there is a metal here and a nonmetal, we're like, okay, if these guys are going to get together, it's going to be one of those situations where the nonmetal is going to beat the crap out of the metal and steal all of its electrons. Okay? So let's go through, let's find strontium on that ionic charge sheet, and we'll find iodine on that ionic charge sheet. And hopefully you'll be able to find it, given the fact that I called it an alkaline earth metal, it kind of narrows down your search. You'll find that strontium in an ionic compound has a 2+ charge. In other words, this thing is a cation. Cations being the things with the positive charge. That means that iodine has to have a negative charge, and we look in the halogen family for iodine, you find it and you realize, wait a second, this thing becomes a 1-. Well, by the way, you can also write +2 or -1. I just write it like this. I don't know why. Just it seems a little backwards. Whatever. So if these two things need to come together, the one thing that must always be true that we learned in the previous video lecture is ionic compounds must have to be neutral overall. Made up of positives and negatives, but when you put it all together at the final step, those suckers better be neutral. And this is a perfect example of where we can kind of use that Crossy trick to help us out. We're going to first write the more obvious part, which is, what elements need to come together. Well, strontium and iodine need to come together. But we're kind of asking what subscripts are going to be needed here, right? The numbers that we write down and to the right are the subscripts that tell us how many of those individual elements are in the compound. So this is where that Crossy trick becomes really helpful. I'm going to circle the number that goes with the charge. I'm leaving the charge alone, right? I kind of know that's there. I'm just using this as a pure trick so that I can always balance out my ionic compounds to make sure that they're neutral. And so what you'll notice is that there's a 1 in front of the strontium, and sometimes chemists get a little lazy, or a lot of the times they get a little lazy, and it turns out you always leave off a 1. You can put it there, but it's not necessary. It's kind of a tell that you're new at chemistry, so I can do a haughty laugh. Look at that silly person that put a 1 in front of, like, tell me to go to hell, right? You probably shouldn't say that in a video lecture, but yeah, you can tell me that. I'm used to it. Now that 2, right, is going to go in front of iodine. So it turns out that the formula for strontium iodide looks like this, right? We're going to learn how to name these things. I know you're excited about that, and that's going to be one of the lab activities for this week, to actually figure out how to name these. For now, I'll just say, yep, it's strontium iodide, and we'll kind of find out why in the lab. It turns out you can do exactly this to any element that's in an ionic compound. You just do the Crossy trick, you end up with a formula, and that's pretty easy. Now when it comes to transition metals though, there's a little bit of a special trick that we have to play sometimes, which I'll show you. But before I do that, I wanted to talk a little bit about what the heck is a Lewis structure, right? And so if we take a look at this formula for strontium iodide, it turns out that Lewis, G.N. Lewis, that was easy to say, came up with this way of kind of representing the way this thing looks. And so let's just erase this, which was just kind of a work area anyway. And once you have the formula, the Lewis structures of ionic compound is actually really, really easy. What you do is you draw each individual element. Right? The formula tells me that I need 1 strontium and 2 iodines. And what we're going to do is we're going to put the charge in, just like was listed off before, but I'm going to list off the charge on each individual element there. The next step is to do what's called a bracket, or what I call a bracket jacket, right? Everything needs a jacket, especially strontium, because strontium has lost its valence electrons, right? They're no longer on strontium. They got transferred to the iodine. And so it's cold without a jacket on once you lose your valence electrons, so you need a jacket. That's why I call those things bracket jackets. It turns out these also get bracket jackets. But the reason that these things need bracket jackets is that they have a whole bunch of valence electrons to hold on to. So they got to keep the valence electrons inside of the jacket. And in Lewis structures for ionic compounds, it's really easy to figure out how many valence electrons are on all your nonmetals because it's always 8, right? And so G.N. Lewis is, I almost call him C.S. Lewis, but that's the Narnia Chronicles guy, the old author. So if I screw up, I apologize for any humanities folks out there. I'm just a ruffian chemist, so I can't be expected to know anything. So what we're going to do is we're going to represent those 8 valence electrons with little dots. And I can't help but sing "Connect the Dots, La 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 La," because that's back from my childhood of Pee Wee Herman. And so what I'm doing here, if you can even see this, is I'm pairing up a bunch of electrons, and I'm doing 4 pairs around the iodine, right? And so this is a way of representing that iodine has its full octet now. That iodine has its full octet. And that's really, each one of those dots just represents a valence electron. Keep in mind, we don't care about the core electrons, the electrons that are inside that aren't doing a damn bit of anything. Well, I guess I shouldn't say that. They're doing a lot, but we don't care about it because it doesn't have to do with bonding. So what we see here is what's called a valid Lewis structure of an ionic compound, right? And so the valid Lewis structure is this guy. And really all it is a way of representing what is involved in this formula. Pretty simple to construct. We're going to go through a couple more examples of that. Okay, so this is number 2 from one of the resource guides from this week. I think it's called the Lewis Structures of Ionic Compounds. And one of the things you'll notice is that now we're going to be dealing with names of ionic compounds, which once again we'll be introduced to a little bit more in one of the lectures for this, one of the labs from this week. So obviously there's an aluminum in here, right? And so it becomes kind of like a fun treasure hunt. Or I don't know how fun it is, but let's pretend it's fun for the time being. You look at your periodic table and you look around for the element known as aluminum, and you figure out what its element symbol is. And it turns out to be Al. And we look at oxide. It turns out that oxygen becomes and has an ID ending, and you kind of drop the igen off of oxygen when you see it in compounds. So that guy is an oxygen. And now what we're going to have to do is look back at our charges list, and hopefully you'll be able to locate these things on the periodic table, figure out what column they're in, and based on that, what their charge is. And so we notice that oxygen has a 2- charge, aluminum has a 3+ charge. So first step of all of these, even if we have to do a Lewis structure, it's always the fact that you got to figure out what the formula is first based on the charges. So we're going to do the crossy trick to determine what the heck our formula is, and we'll write our correct formula over here. And what we end up with is 2 aluminums and 3 oxygens that are in that compound. At this point, we know how to do a Lewis structure. So all we do is we look at how many aluminums I need and how many oxygens I need, and we're going to put each one of those cations and anions down, right? And so this is going to be where I do the actual Lewis structure. That was just the formula. What I'm going to do is list off the 2 aluminums that are required. I'm going to list off all of the oxygens that are required. I'm going to remember that I need bracket jackets for everyone. I'm going to remember that I need to indicate the charge of all the anions and cations. So aluminum, we decided, was a 3+. That is considered the cation. And then oxygen is all going to be 2-. Last step is to connect the dots, la 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 la. I guess you don't connect them, you just put the dots, la 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 la. And you make sure that you put 8 on each one of those oxygens, which is a way to kind of communicate that you know that's the nonmetal, you know that's the thing that gains electrons, you know that's the thing with the minus charge, even though the minus charge is already listed. Lewis structures of simple ionic compounds. That's all there is to it. Before we end this particular video lecture, it's probably important to consider something special that sometimes happens when you're trying to figure out formulas or Lewis structures for compounds. And that's when you see some sort of transition metal. Keep in mind that the transition metals are in what I call the sphincter tightening region, where they all have variable valences. Many of them have variable charges for that reason. So it's probably good to just talk real briefly about, what do you do if you encounter one of these things and you have to make a compound out of something that is a metal in the transition metal region and then just our normal nonmetal. Well, it turns out that as written, there's not really enough information. So usually what happens is in some way you'll indicate what the charge on that transition metal is. If you look at the charge sheet, you'll notice that there's a couple of different options for chromium. In fact, there's actually many more than just that. But how do you figure out what the charge is? Well, it turns out there's 2 ways. Well, there's actually several ways, but 2 ways that we'll talk about right here. If you're looking at the name, what you'll often see is something called a Roman numeral. So let's say that you were looking at the name of this compound and it said chromium 3, and then this thing with a minus charge is called a sulfide, right? You drop the and add an ide, and so that's the name of that particular compound. And so you'll notice the presence of this Roman numeral. What the heck does that correspond to? Well, it turns out a Roman numeral always corresponds to what the charge on the metal is, and almost never corresponds to the number of metals in your formula. And that's something that drives students bonkers. So just put it somewhere in big letters and circle it and put explosion marks around it, that the Roman numeral is indicating what the charge of the metal is. So what does that mean about drawing our formula? Well, it actually makes things a heck of a lot easier, because now we can just draw a chromium when we're trying to figure out the formula and say, oh man, yeah, of course, it's a 3+ charge. Just wrote on my shirt. Sulfur, right? We look that up, find it in what's called the chalcogen family, oxygens family, which most of the time has a -2 charge. And so now we know that this chromium 3 sulfide, we know what the charge is on the chromium, what the charge is on the sulfide, and we do what we call the old Karasi trick to figure out what the formula is. So it turns out that the formula for chromium 3 sulfide looks like this. One thing that I want to note is notice that that Roman numeral 3 does not correspond to the number of chromiums. This is something that you will all screw up quite often if you don't write this down somewhere. That corresponds to the charge, right? Not to the number of chromiums. Really confusing. So that's our ionic formula. And so now what we can do is we can just do all those Lewis structure rules. And so I'll just pause the video for a second so you don't have to watch me putting dots on a board. Okay, right here in this blue box right here, or blue blob, or whatever the heck you want to call it, I've got the valid Lewis structure for chromium 3 sulfide. Probably what we should talk about is, well, what if the other charge of chromium, the other really popular charge of chromium, is a 2? What would that formula look like? What would that Lewis structure look like? So bear with me in just a second. So the other charge state of chromium is a chromium with a 2+ charge, indicated by that Roman numeral. So let's see what that does to our formula. As you might expect, some changes will be afoot. Right, we already know the charge on a sulfur is a 2-, and charge on chromium 2+. Chromium 2 is a chromium 2+. You'll notice that as written, that's perfectly balanced, so we don't have to do anything. If you want to do the Karasi trick on this, that's okay. Again, that's just like if you called this, instead of CRS, if you called it CR2S2, again, that's just kind of like a haughty laugh, like you didn't reduce it to the lowest number ratio, which is kind of one of those esoteric rules in chemistry. But I don't care. Either way is perfectly acceptable to me. So you'll notice that that thing, chromium 2 sulfide, is right here. And I won't insult your intelligence by showing you the Lewis structure, because it's super easy. One chromium with a 2+ charge, one sulfur with a 2- charge, bracket jacket, put a bunch of electrons around the sulfur. There you go, you're good. 8 electrons, I should say. So this is chromium 2 sulfide. You'll remember that when we saw the other one, chromium 3 sulfide, we saw a formula that looked like this. So you might wonder, well, what does it matter? Well, it turns out this has completely different chemical and physical properties than that. So it really does matter. Keep in mind, back when we looked at the definition of substance, they have to be they have to have definite proportions. Otherwise, if you don't maintain your definite proportions, you totally change the chemistry of whatever your substance is. You actually make another substance. So these are two very different things. All resulting from the fact that you've got a different plus charge there. Before we end talking about Lewis structures, I should mention there was kind of one other question type that asks you to do a Lewis structure for the uncharged element. So if you're going to do the Lewis structure of an uncharged element, it turns out to be pretty simple. So keep in mind, we're not talking about compounds here. These are sometimes called the parent elements, when they then lose their electrons or gain their electrons to become cations or anions, respectively. But just in case somebody says, give me, let's say, the the Lewis structure of an oxygen atom, or something like that. Right? Notice that we're just talking about an oxygen atom. We're not talking about oxygen in an ionic compound. We're not talking about oxygen in a covalent compound. So what do? Well, it turns out this is very simple. If you remember the valence electron count of all your different columns, right? We just number 1 through 8 across the top, skip the sphincter tightening region. You'll notice that oxygen is in column 6, also called the chalcogens. And so what we're going to do is we're just going to write an oxygen, and we're going to pair up a few electrons, and then we end up with something that looks like that. So that guy right there is considered, we'll say uncharged oxygen atom, and sometimes you'll hear this called a parent. Because this is what oxygen kind of starts off as in its uncharged state. You'll notice that I didn't put 8 electrons there because we don't have 8 electrons yet, right? This is just the parent. This is what it starts as. So in a certain sense, this is a much more simple way of doing atomic structures, where you just ignore, like if I said, hey, draw an oxygen atom, right? This ignores basically everything except for the most important part of that in chemistry, which are the valence electrons. So once you've got this parent, then if it's going to be involved in an ionic compound, we could show it with 8 electrons and a 2- charge. When we finally get to doing covalent Lewis structures, being able to kind of figure out how many electrons you start with is pretty important before all that bonding happens. So that's just something that I would kind of be able to commit to my, my skill set. For instance, let's just pick out something that is a metal, right? Let's say that instead of doing a Lewis structure of an oxygen atom, instead we want a calcium atom. Well, same thing. You look at the numbers across the top. You say you're in the second row. Therefore, we're going to put 2 dots on there. And I should mention also that it doesn't matter where you put your dots around the atom. It honestly, it doesn't even really matter that you pair them up like this, as long as you put 6. It just makes my eyes bleed less. And there are some different reasons that we'll start to talk about a little bit why you might pair them. So honestly, as long as you showed these 2 electrons anywhere around calcium for its parent ion, all is good.